Okay, let's dive in. Today, we're exploring a timescale that's just incredibly, incredibly small. We're talking about attoseconds.
Yeah, and when we say small, it's almost impossible to really picture. I mean, think about this. There are about as many attoseconds in one single second
Hmm.
as there have been seconds since the Big Bang, since the entire universe began.
Wow. Okay, so you're taking the whole age of the universe and squishing it down into 1 second. That's mind-boggling. So why? Why spend, decades trying to see things that happen that fast? What's going on down there?
Well, because that tiny, tiny slice of time, that's where electrons live, dynamically speaking. It's the timescale of electron motion. Attosecond science is all about revealing how these electrons move, how they behave.
And that electron behavior, it's not just some like abstract physics thing, right?
Um,
It actually
well,
matters.
absolutely. It's fundamental. Those electron dynamics, they determine, well, basically everything. Properties of materials, how chemical bonds work, how light interacts with stuff, the underpinning of technology, biology, our whole physical world.
Right. And for so long, we could only theorize about these motions because they were just too fast to see. So the huge achievement we're digging into today is that we can now actually generate light pulses, short enough attosecond pulses,
Oh.
develop ways to measure them, which is a whole story in itself, and even shape them into pulse trains or like single isolated bursts.
Exactly. And it's not just about seeing anymore. It really opens the door to maybe even controlling electron motion directly, which is pretty profound.
And we're getting our insights straight from the source, right? From the Nobel lectures of the scientists who made this possible.
Yes, precisely. We've looked closely at the work and the lectures from Anne-Louis Ley, Pierre Agostini, and Ferenc Krausz. Their contributions were absolutely key.
So our mission for this deep dive,
Yeah.
let's trace that journey. From the surprising discoveries, the theories that explain them, the tech breakthroughs, all leading to generating, measuring, and using these attosecond pulses. And crucially, why it matters so much to be able to see electrons in motion.
It's quite a story. And, like a lot of big breakthroughs, it builds on what came before. It really starts with one essential tool.
You mean the laser?
Exactly. Invented back in 1960. Lasers gave us light that was intense enough and eventually short enough to actually, poke at matter hard enough to see interesting things happen on that tiny scale.
And focusing that intense laser light, that immediately kicked off new fields, didn't it? Like nonlinear optics.
Right. Where materials don't just respond proportionally to the light, suddenly you see atoms absorbing multiple photons at once or spitting out light at totally new frequencies.
Like doubling the frequency, second harmonic generation, that kind of thing.
Precisely. And people started studying atoms in really strong laser fields. That led to things like multiphoton ionization, kicking an electron out by absorbing several photons. Pierre Agostini was actually a key figure there early on. He observed something called above-threshold ionization.
Above threshold.
Yeah, where electrons absorb more photons than they actually need just to escape the atom. They soak up extra energy from the strong field even after they're technically free.
Okay, so these were important steps. But the direct road to attoseconds, that started later, with Anne Lhuillier's work in the late 80s.
That's right. And interestingly, she wasn't even looking for attosecond precursors initially. She was studying fluorescence light emitted by atoms after being excited by strong lasers.
But she found something else entirely.
Completely unexpected. Instead of just a diffuse glow, she saw this beam of light shooting out in the same direction as her laser. But this new light was made up of incredibly high frequencies, high-order harmonics of the original laser.
High order, like way beyond just doubling or tripling the frequency.
Oh yeah, we're talking the 13th, 15th harmonic, all the way up to the 31st harmonic in her early experiments with an infrared laser, and from just a simple gas target.
And wasn't just the number of harmonics surprising, but also how bright they were.
Exactly. That was the really bizarre part. Normally, you'd expect higher harmonics to get weaker and weaker very quickly, but she saw this plateau, a whole range of high harmonics that had roughly similar intensities. Then, suddenly, a sharp cutoff where they just stopped.
That didn't fit the standard theories at all.
Not the simple ones, no. It didn't match the usual perturbative way of thinking about nonlinear optics.
And they were only odd harmonics, right? 13th, 15th, 17th?
No.
Not 14th, 16th?
Correct. Which is a telltale sign related to the symmetry of the atom and the laser field interaction. And, importantly, when you multiply an infrared frequency by, say, 30 times?
You end up way up in the spectrum.
Way up. You get light in the extreme ultraviolet, the XUV range. And XUV light is key because, well, its frequency is much higher, meaning its potential timescale is much shorter.
It's like hitting a low note on a piano, and suddenly the piano itself starts ringing with all these incredibly high-pitched overtones seemingly out of nowhere.
That's a great analogy. And generating this XUV light efficiently involves not just one atom doing its thing, but getting millions of atoms in the gas to emit their light waves together in phase so they add up constructively.
Ah, the phase matching aspect.
Right. Early computer simulations, solving the quantum mechanics, could reproduce the plateau and the cutoff, which was good. But why the physical picture behind how the atom actually did this extreme frequency conversion was still pretty murky.
And around this time, people started thinking, if you have all these high harmonics, this broad range of frequencies, could they add up?
Exactly. And it was a big if back then, if their phases were locked together in just the right way, could they interfere to create incredibly short pulses of light and time?
Pulses much shorter than regular lasers could make.
Yeah.
Because you need lots of frequencies summed up coherently to make a short pulse.
Right. Precisely. The physics is the same. Summing waves with different frequencies but controlled phases makes them pile up constructively at specific moments, creating a sharp peak. If the waves are harmonically related and phase-locked, you get a train of very short pulses.
And the timing was kind of perfect, wasn't it? Because laser scientists had sort of hit a wall trying to make pulses shorter than a few femtoseconds.
They had. You were limited by the oscillation period of the light itself. To go shorter, you fundamentally needed higher frequencies. And that's exactly what high harmonic generation offered, much higher frequencies, and a whole bunch of them.
But there was a snag. The initial theories, they didn't look promising for those phases.
No, that was the bad surprise, as Le Huillier called it. Early calculations suggested the phases of these harmonics would actually be kind of random relative to each other, not locked.
Which would mean no sharp pulses. Just a mess.
Just diffuse XUV light, basically. It looked like this amazing source of high frequencies might not actually deliver the goods for making attosecond pulses. The issue turned out to be that the electron's interaction with that strong laser field is really complex, more complex than the first models captured.
Okay, so how did they crack that?
Yeah.
How did they figure out the phase problem and, fix it?
The big breakthrough was the development of what's called the three-step model. Came from a few groups independently, more or less. And it provides this really elegant, almost semi-classical picture.
3 steps. Okay.
Step 1. The intense laser field basically warps the atom's potential barrier enough that an electron can quantum mechanically tunnel out, even if it doesn't classically have enough energy to just jump over.
Right, tunneling. Got it.
Step 2. Once it's outside, the electron gets grabbed by the laser's oscillating electric field and accelerated away. But then, as the field flips direction...
It gets pushed back towards the atom.
Exactly. It gets driven back towards its parent ion. Step 3. If it recombines with the ion, it releases all the energy it gained from the laser field, plus its original binding energy, as a single high-energy XUV photon. That's your harmonic light. And this whole thing repeats every half cycle of the laser field.
Tunnel, accelerate, recombine. Okay, that makes sense for making the XUV photons. But how did that model solve the phase problem? Why weren't the phases locked initially?
Because the model revealed something crucial. For any given harmonic energy, there isn't just one way for the electron to get back to the atom. There are typically 2 main paths or trajectories through that oscillating laser field that end up with the right recombination energy. One takes a shorter time, one takes longer.
2 different paths for the same energy.
Yes, and the light emitted from electrons taking these different paths interferes. Critically, because these paths experience different amounts of the laser field's phase evolution, their interference messes up the overall phase relationship between the harmonics emitted by the whole ensemble of atoms.
Okay, and could they actually, prove these different trajectories existed?
They could, by looking very carefully at where the harmonic light went, its spatial profile. It turned out that light generated via the shorter electron trajectories tended to form a more focused, collimated beam, while light from the longer trajectories was more divergent, spread out. And that was a huge insight. Because it meant you could physically separate them. By doing something as simple as putting a small aperture, basically a pinhole, in the XUV beam path after the gas jet.
You could block the spread out light and just let the focused beam through.
Precisely. You could select mostly the light coming from just one type of trajectory, the short one, usually.
So a pinhole. A simple pinhole helped unlock attosecond science.
Fundamentally, yes, guided by the theory, of course. That act of spatial filtering was essential. When they redid the phase calculations, only considering the short trajectories, the prediction changed completely. And suddenly, the theory predicted beautifully phase-locked harmonics, which meant attosecond pulse trains should be possible after all.
Wow, okay, so theory finally said, yes, you can make them. But then, how on earth do you measure something that fast? How do you even know you've succeeded when your pulse lasts only a few hundred attoseconds? Your standard detectors are like glacial in comparison.
Right. That was the next mountain to climb. It needed totally new measurement ideas, plus continued leaps in laser technology itself. The 90s were huge for lasers techniques like chirped pulse amplification, T-sapphire lasers taking off, Kirlin's mode locking.
Making the driving lasers shorter and much more powerful.
Exactly, providing the necessary engine for efficient high harmonic generation. And the tools to analyze the harmonics got better too. But yeah, measuring the duration and time, that was the missing piece.
And this is where another ingenious technique comes in. Rabat.
Rabbity, yes. Sounds a bit whimsical, I know.
Definitely sounds like a bunny. What's it stand for?
It's reconstruction of attosecond harmonic beat by interference of two-photon transitions.
Ah, less cute. Definitely more descriptive. Okay, so what's the idea?
The core concept is you take your attosecond pulse train, the thing you want to measure, and you overlap it in time and space with a weak copy of the original infrared laser field that you used to make the harmonics.
Okay, got the setup.
Now, an atom in your detector absorbs one of the high-energy harmonic photons from the XUV train. That knocks out an electron's standard photoionization. But critically, while that electron is escaping, it can also interact with that overlapping infrared field. It can absorb or even emit an infrared photon.
Ah, so it's like a two-photon process using one XUV photon and one infrared photon.
Exactly, a two-color transition. And this interaction creates little bumps, new peaks in the energy spectrum of the electrons that come out. They're called sidebands, and they appear right in between the main energy peaks you get from just absorbing the harmonics alone.
Okay, sidebands appear. What's the clever part?
The clever part is that the strength, the amplitude of these sideband peaks changes, it oscillates up and down as you very precisely adjust the time delay between when the attosecond pulse train hits the atoms and when the infrared field is there.
So you scan the delay between the two pulses.
You scan the delay, and by carefully measuring how those sideband signals oscillate as a function of that delay,
You can figure something out about the attosecond pulses.
you can directly extract the phase difference between adjacent harmonics in your XUV pulse train. And since you only get a nice, short pulse train if those harmonics are properly phase-locked.
Measuring their phase relationship tells you if you have attosecond pulses and how short they are.
Exactly. It confirms their existence and lets you mathematically reconstruct their duration. The first measurements using Rabbit back around 2001 confirmed pulse trains with durations around 250 attoseconds, later pushed down closer to 170, 200. A major milestone.
Incredible. So Rabbit nails the pulse trains. But what if you want just one single attosecond pulse, not a whole series of them?
Right, that was the next big goal. And the key to that was pushing the driving laser pulses to be even shorter, getting them down to just a few oscillations of the light field, maybe just 5 femtoseconds or less, or even ideally down to a single optical cycle.
Whoa, a laser pulse that's basically just one wiggle of the electric field?
Pretty much. And with extremely precise control over the exact shape of that wiggle, something called the carrier envelope phase, or CEP, Ferenc Krausz and his group were real pioneers in developing the laser technology and techniques to achieve this.
So if your driving laser pulse is that incredibly short,
Then the whole high harmonic generation process itself gets confined to maybe just 1 or 2 half cycles of that driving field. It only happens during the absolute peak of the laser pulse.
so the emission itself is naturally limited in time.
Exactly. And that temporal confinement, combined with some spectral filtering to select only the highest energy harmonics from the cutoff region, which are generated only at the very peak, that makes it possible to isolate just the single burst of attosecond XUV light.
Okay, so you can make a single pulse. Now, how do you measure that? Is Rabbit still the way?
Not directly for a single pulse. For that, they developed another brilliant technique, conceptually kind of like an incredibly fast streak camera, but using the laser field itself, often called light field-driven streaking.
A streak camera, using light itself.
Yeah. The idea is You fire your single isolated attosecond XUV pulse at your target atoms, again, knocking out an electron via photoionization. But you do this while that intense, super short infrared laser pulse, the fuse cycle 1, is also present, overlapping in time.
Okay, so the electron gets freed by the attosecond pulse, but it's immediately born into this really strong, rapidly changing infrared field.
Precisely. And here's the key bit. Depending on the exact instant within the infrared laser cycle that the electron is liberated by the attosecond pulse,
Uh-huh.
the strong electric field of that infrared laser, which is oscillating extremely fast, will give the electron an extra kick as it leaves. It'll either speed it up or slow it down, depending on whether the field is pointing one way or the other at that precise moment.
So the final speed or momentum of the electron gets stamped with information about exactly when it was released relative to the laser field's oscillation.
You got it. The laser field acts like an ultra-fast stopwatch or phase clock. By measuring the electron's final energy or momentum distribution, you can map out how many electrons were released at each instant relative to the known oscillation of the laser field.
And since you know the timing and shape of that strong laser field very well.
Right, you can calibrate that separately. So measuring the final electron momenta allows you to work backwards and figure out exactly when the electrons were released, and that directly reveals the temporal shape, the duration of the attosecond XUV pulse that freed them.
That's genius. So it's a direct time domain measurement.
Yes, it gave the first really clear, unambiguous measurement of isolated attosecond pulses. And it's the technique that's been used to push the records down. I think the shortest reported now is around 43 attoseconds.
Oh,
Just
wow.
incredibly short.
Unbelievable. Okay, so let's recap the journey.
That's like,
Started with seeing these weird high harmonics unexpected. Then figuring out the three-step model to explain how they're made. Solving that tricky phase problem using trajectories and spatial filtering.
all right, the pinhole trick.
Then massive leaps in laser tech to make fuse cycle pulses, and finally inventing totally new ways to measure things, like rabbit and streaking. It's an amazing scientific story. But now that we can do this, what's the payoff? Why is seeing things on the attosecond scale so important?
Because, like we said at the start, that's the time scale of the electron. These are the fundamental motions that drive chemistry, material properties, everything. Now, instead of just inferring, we have essentially a camera fast enough to take snapshots or even make slow-motion movies of electrons in action.
Like you could actually watch an electron tunnel out of an atom,
Right.
or see charge shifting around in a molecule during a reaction.
Exactly that kind of thing. People have used these techniques to study fundamental processes like photoionization in incredible detail. Finally measuring, for instance, how long it really takes an electron to escape an atom after it absorbs a photon.
Is there a delay?
Yes. And it's measurable, down to tens of attoseconds. And it can even be slightly different depending on which electron shell it comes from within the same atom. They've used the streaking technique to measure these tiny time differences with amazing precision.
I remember reading about an analogy they used, like a clock face, where 1 hour was just 1.3 femtoseconds.
Yeah, 1,300 attoseconds.
But they could measure the time difference between two hands on that clock down to attoseconds. It really hammers home the precision.
It does. And attosecond pulses let us probe more complex stuff too, like what happens when a strong laser field rips out two electrons from an atom. It seems the first electron leaving can influence the second one, maybe by coming back and colliding with it. Attosecond control lets you start to disentangle those correlated dynamics.
Okay, so huge for fundamental science. Are there more sort of practical applications starting to show up?
Absolutely. One area that's already benefiting is manufacturing, especially for making the next generation of computer chips.
How so?
Well, high harmonic generation itself is a pretty convenient tabletop way to make extreme ultraviolet light, XUV light. And you need XUV light for advanced lithography, the process used to etch the tiny patterns onto silicon wafers.
For making smaller transistors.
Exactly. To get features down to 10 nanometers or even smaller, you need shorter wavelength light sources. High harmonics provide a coherent XUV source that's being used and developed for metrology and inspection in that industry, and potentially for the etching itself.
So the light source technology born from attoscience is directly helping build smaller, more powerful electronics.
Precisely. And looking a bit further out, the attosecond pulses themselves might revolutionize electronics. Imagine being able to apply an incredibly strong electric field to a material, like a semiconductor, but have that field only last for, say, 500 attoseconds.
Just a very brief, strong kick.
Right. You could potentially drive electrons into new states or make them switch states incredibly fast, much faster than current electronics allow, maybe without even heating up the material because the pulse is so short. People talk about petahertz scale signal processing thousands of times faster than today's gigahertz electronics.
Wow. That would be transformative for computing and communications.
It could be. And then there's another application area that's generating a lot of excitement, maybe the most potentially impactful in the near term: medicine.
Medicine. Attoseconds and medicine. How do those connect? That seems like quite a leap.
It does, but the connection is through analyzing molecules. The idea is to use light pulses to get a detailed fingerprint of the complex mix of molecules in a biological sample, like blood plasma.
Okay.
They take a sample and hit it with one of those very short, intense, single-cycle infrared laser pulses we talked about earlier. This pulse gives the molecules in the sample a sort of vibrational kick.
Makes them wiggle.
Essentially, yes. And as they vibrate, the molecules themselves emit their own faint infrared light field.
And that emitted light is the fingerprint. It depends on exactly what molecules are there and how they're vibrating.
Exactly right. It's an incredibly complex signal containing information about all the different molecules present. The crucial step is that they can actually measure the precise electric field waveform of this faint molecule-emitted light with attosecond level time resolution.
Using techniques related to the streaking camera.
Similar principles, yes. Extremely sensitive detection of electric field oscillations over time. They look at the exact shape and timing of the wiggles in that emitted field.
Okay, so you get a detailed molecular fingerprint. How does that help detect disease?
Because diseases, even in their very early stages, cause subtle changes in the body's biochemistry, and those changes are reflected in the molecular composition of your blood.
Ah, so the fingerprint changes if you're sick.
That's the idea. These biochemical changes lead to small but potentially detectable alterations in that emitted infrared fingerprint signal, tiny shifts in the timing of the oscillations, maybe changes in the shape of the waveform measured down to the attosecond or femtosecond level. They analyze things like the precise time between the zero crossings of the measured electric field.
And are they actually seeing differences? Can they tell healthy blood from diseased blood this way?
The results are starting to look very promising. There have been studies showing they can distinguish differences in these time domain fingerprints for various conditions. Perhaps most notably, several groups have shown promising results in distinguishing blood samples from patients with certain cancers, like lung cancer, even early stage ones, compared to healthy control groups.
Wow, so by looking at these incredibly subtle, fast variations in the light emitted by blood molecules, you might be able to spot something like cancer much earlier than we currently can.
That is the profound hope, yes. The vision is this could lead to a new type of diagnostic tool, maybe a quick, non-invasive blood test based on this light field fingerprinting that could be used for large-scale screening. Finding serious diseases earlier could make a massive difference in treatment outcomes and potentially save many, many lives. It's still very much an active area of research, but the potential is huge.
That's incredible. It really shows how pushing the absolute frontiers of measurement, just trying to see the fastest things possible, can spin off in directions you might never have predicted, from fundamental physics to maybe even changing how we approach healthcare.
It really does. It underscores the power of just fundamental curiosity, doesn't it? Understand how the world works at its most basic levels often leads to the most unexpected and powerful applications.
So we've journeyed from the invention of the laser, through the surprise of high harmonics, the cleverness of the three-step model and measurement techniques like rabbit and streaking, all the way to potential applications in nanomanufacturing and even early disease detection. We can now access the attosecond world.
A world previously hidden, where the fundamental dance of electrons dictates so much of our reality.
So you've now had a glimpse into the fastest events ever, directly observed and even controlled by humans, a time scale that was pure science fiction just a few decades ago.
Which leads to a final thought. Considering just how much electron dynamics govern materials, chemistry, biology, what other fundamental secrets, what completely new technologies might still be waiting to be discovered now that we've finally opened the door to this attosecond realm. What else is happening in the world around you right now on that time scale that we're only just beginning to see?